Good day, everyone. Can you guys see what I'm projecting right now?
Yes, yes.
Okay, I want to welcome you to my lecture today. And you remember last time we did something on the composition of the response variable. But the essence of today's lecture is just to be able to do what I call diagnostics in simple linear regression. And what do we mean by diagnostics? What we mean by diagnostic is just that, okay, I got a model and I actually want to evaluate my model. I want to put my model to test before I can actually use this model to make prediction. And before I get started today, I want to tell you that the practical assignment instruction have been uploaded with deadline set for practical 1, practical 2, practical 3. Okay, check for that. And you know what? In tomorrow's lecture, I'm actually going to walk you through the practical assignment guide. I've already uploaded that. You can read that. But I'm going to talk more about practical assignments in our lecture tomorrow. Okay, so just to tell you, the practical assignment has already been uploaded. I want you to read that, read the instruction, then we're going to talk about it tomorrow. Okay, so like I said, today we're focusing on diagnostics for simple linear regression. Okay, and the important topics, that we're actually going to be focusing on today will be residual plots. Okay, so then we're going to also discuss some unusual observations. Okay, I told you before that we are in a world where we actually want to have control over our environment. And you know what? To have a control over our environment, because our environment is, there's a lot of variation. Because of that, we want to build a model, a statistical model per se. And it means we are actually want to use model to capture reality. Okay. And the fact remain that model okay, model that we're using, you know, does not really capture this reality exactly. There's always going to be unexplained variation. Okay, there's always going to be unexplained variation. So the only way to tell if our model is good is to be able to have is to be able to investigate whether the assumptions underlying a particular model is actually met, because it is only when assumptions are not violated, it is only when assumptions are met, that we can actually use our model in policy formulation. Okay, and that is the reason why we're actually going to have analysis of residual. Okay, and we are also going to be investigating whether there is a presence of unusual observation. Okay, and that is going to be our focus today. Okay, uh, let us have a guess. Okay, we we actually want to have a guess on correlation. Okay. And of course, if I have two variables, okay, and I actually want to know whether they got a relationship together, and if I actually want to know the extent of the relationship, of course, what we always do is to find correlation. Okay, so correlation is a measure of strength of linear relationship between two variables. I want you to look at the word linear. Okay, now the question is, if the relationship between two variables is not linear, can I actually find correlation? Okay, uh, we don't find correlation when the relationship is not linear. Okay, I'm going to say that again. And I'm actually going to walk you through the reason today why, if I'm talking about correlation, I can only use that to measure the strength of the linear, look at the word linear, okay? Linear relationship between two variables. In a situation where two variables are not linearly related, I can't find correlation. Then maybe I got to do something to convert the relationship to linear, okay? As time goes on, we're actually going to be talking about non-linear. We're going to be talking about how non-linear relationship can actually be transformed into a linear relationship. Okay, we're going to discuss that in the subsequent lecture. Okay, um, if that is the case, I got its data set. Okay, where I have two variables. Okay, and I decided to plot that. Okay, uh, using this is scatter plot. Can you guys see what I'm projecting right now?
Yes.
Okay, thank you so much. Okay, so when you take a look at what I have right here, okay, we are looking at the relationship between these two variables and believing that I can only find that relationship if I have a straight line. Okay, good job. If look at this particular data set 2, the relationship here is not linear because when you look at, there's a curve. Look at that. Let's look at a curve. Okay, so this is not linear, but if you look at the one right here, okay, this is more or less like a linear. Okay, so if you look at the data set 1 and this data set 2, in terms of the relationship, okay, one is actually showing a linear relationship and the other one is actually showing non-linear relationship, because anything other than linear is what we call non-linear. And you know what? There are different kinds of non-linear relationship. We're going to talk about them in the subsequent lecture. Now, uh, the practical assignment that I've given you, I'm actually going to talk about the practical assignment tomorrow, uh, where you need to work on the data set, and that data set has, actually have to come from your discipline. It has to be data set uh, from where you are majoring, okay? And you know what? You're actually going to work on a causal relationship where you actually need to investigate, just like what I'm doing right now, between the set of variables. You actually need to know whether you have a straight line relationship or you don't have a straight line relationship, okay? And that's exactly what I'm doing right now. But you know what? Uh, Tomorrow, I'm actually going to talk more about practical assignment. Okay. Uh, if you look at the next, if you look at the question, I said which one has a higher correlation? Okay, that is a question right here. Which one has a higher correlation? Let me tell you something. if you take a look at the two, I told you something the other time that um, if you have a linear relationship, you can actually find correlation. And you know what? If the relationship is not linear, uh, of course there is something that we can do. Okay, we can achieve linearity through transformation. I'm actually going to walk you through that in the future. Okay, now we decided to find a correlation here and here, and we got 0.82. And because of the fact that correlation determines if we want to, there are two things that we actually want to have before we can actually find correlation. What I'm trying to tell you this is that correlation does two things. Number one, with correlation, you'll be able to know the direction of the relationship. Okay, you'll be able to know the direction of the relationship between the two variables or between the two or more variables. And not only that, you will have the direction of relationship, you will also have the opportunity to know the strength of the relationship. I'm actually going to make use of my whiteboard now. I'm going to have a new share so that for those of you who may not hear me clearly, uh, I'm going to tell you the essence of the correlation analysis. So for correlation, are you guys seeing my whiteboard now?
Yes.
Thank you so much. Number one, the correlation will enable us to know the strength. Okay. And number two, then we'll be able to figure out the direction. Okay. So if I'm looking at the relationship between two variables, okay, what I actually need to do is to talk about if is to obtain the correlation. Okay, then the correlation is actually going to give me the strength and the direction. Okay, so if I'm talking about if I'm talking about strength and the direction in correlation, what am I going to see in the correlation value before I will be able to tell about the strength and the direction of the relationship? I'm going to show you right now. Okay, uh, what I want to show you right now is just that when correlation have a value between -1 and 1, okay, it has a value between -1 and 1. If a correlation equal to -1, that's a perfect negative. If a correlation is +1, that's a perfect positive. But let me tell you something. Because of the fact that we live in an uncertainty world, we are not going to have a perfect correlation, okay? But we're actually going to have a value that lies between -1 and 1. It's going to be greater than -1, and it's actually going to be less than 1, okay? And you know what? The sign that we have, the sign of the correlation will actually tell us the direction. The direction in the sense that whether the relationship is positive or negative, okay? So the sign. Can you guys see what I'm projecting right now? Guessing relationship, guessing correlation. Can you guys see it right now?
Yes.
Okay, thank you so much. So if you look at the value here, it's actually assuming that, okay, because this is a positive sign, okay, and that indicates, okay, the direction, okay, the direction here is positive, okay. Now, because of the fact that I have a value that is very close to 1, and that will actually tell us that, okay, this is telling us the strengths, okay. It's telling us that, okay, the relationship that exists though is positive, but uh, this relationship is very, very strong, okay. So what I'm just wanting to know on this side slide. It's just that, okay, correlation tells us two things. It tells us the strength and it tells us the direction. So it tells us the direction by the kind of sign that we have, whether positive or negative, and it tells us the strength based on the figure we have. If a figure is very close to 1, but refer to that as strong, if a figure is very far from 1, we're going to refer to that as weak. Okay? And that was why we said the correlation measures the strength of the linear relationship. Therefore, it assumes that the model is linear. Okay? And when that assumption is violated in figure B, the correlation does not make sense. So what I'm trying to tell you, the assumptions of linearity is violated in data set 2. Okay? And in data set 2, even if I make use of R, okay, to compute my correlation between the Y2 and the X2, you know, when you do that for this data set, you're still going to have 0.82. And when you do that to this, you're still going to have 0.82. But the fact that the structure of this data set is not linear in terms of relationship, the value that come out does not make sense. Okay? That value does not make sense. But that very value makes sense right here because this is a linear relationship. Because the assumption of a correlation is that we are actually talking about linear relationship. Okay, there must be a linear relationship between the variables under investigation before the correlation value can actually make sense. Okay, in a situation whereby you got to plot this way and you realize that the relationship is not straight line but it's a curve, you get what I mean, then finding correlation will not make sense. Okay, and this is part of regression diagnostics because if I have already obtained the value of my correlation, okay, because when you run a linear regression, correlation will be part of the regression output. Okay, so so if it is part of regression output, before you can actually interpret that correlation result, then you need to have a scatter plot to be able to see where the shape, you know, the shape of the relationship. Okay, if it is linear, then that makes sense. You can actually interpret that. If it is not linear, just like the way the data set 2 is actually showing right now, then it doesn't make sense. Okay, it is not all values, it is not all results that make sense. Okay, and because we have assumption. Okay, when we compute everything anything in statistics, we need to revisit our assumption. Okay, we actually need to see whether assumptions are violated or not. Okay, now uh the next thing we want to talk about is the numerical summary of a regression model. Okay, numerical summary of a regression model. That is what we want to talk about now. Okay, you've fitted a linear regression model. Okay, this time around, you are not only looking at the relationship, but at the same time, you are looking for a way to predict a variable from the other one. Okay, you know, that is a difference between regression and correlation. Okay, the correlation will do a good job of trying to tell us the direction and the strength of the relationship between two variables. But you know what? The correlation cannot tell us how a variable can be predicted from the other one. Okay, but what tell us is regression. Okay, regression do the job of prediction. Okay, now we've run our regression, but the question now is, what will you conclude based on the model summary? Okay, and the question is this simple linear regression model a good fit to the data? Okay, we don't just use a model to predict like that. We need to do a lot. Okay, we actually need to evaluate the model. Okay, so what we are trying to do right now is model validation. Okay, if you don't do model validation, if you go ahead to use your model in policy formulation, or to use the recommendation from your model in policy formulation without, you know, uh, investigating whether your model is good, then you are likely to take the wrong decision at the end of the day. Okay? And you know what? We don't want to regret. We don't want to have a decision. We don't want to take a decision today and actually regret our decision at the end of the day. Regret taking a decision at the end of the day. And that is the reason why we actually need to subject our model into diagnostic testing. Okay. Now, uh, if you look at what I have right now, I actually have the linear regression output. Okay. So this is a linear regression output. Okay. And the question now is, before I started using, um, making use of this output, before I started using the model, there are some, measures right here on this output that actually tell us about how we can actually investigate whether assumptions are violated or not. Okay. Now, like correlation, most numerical summary results can be invalid when assumptions are violated. Okay. And that is the reason why we actually need to investigate assumptions. I remember I told you the other time, I said model is as good as assumption putting into a model. Okay? Model is as good as assumption putting into a model. Okay? So if what makes a model to be good, it's just that we have been able to investigate such model, and we find out that the assumptions are not violated. Okay, because when the assumptions are violated, okay, then the correlation results, the regression result that we got will not make sense. They will not be valid. Okay. Now, uh, I want to show you a different plot right now. I got four data sets, four different data set. Uh, if you look at the two variables right here, it's different from the two variables right here. It's different from two variables right here, and it's different from two variables right here. Okay, and you know what? I actually plotted uh, the two variables in each data set. And why am I doing that? I'm actually doing that to have the clear picture of the relationship between the variables. Okay, and you can see what we have in data set 1, you can see what we have in data set 2, you can see what we have in data set 3, you can see what we have in data set 4. Okay, I want to tell you right now, uh, the data set 1, if you look at this one, there is no issue in data set 1. The data set 1 is linear. Okay, though the relationship in the data set 1 is not perfect, because we don't expect relationship to be perfect, because if the relationship is perfect, all these points, all of them will be on the straight line. Okay, so uh, we're in a world where uh, we don't have a perfect model anywhere. So we don't expect uh, all the variables, I mean all the points to be on the straight line. Okay, so this is fine. Okay, this really makes sense. Okay, so there's a linear relationship that exists right here, and you know the data set, the data point, they're actually clustered around. You see that now. But when you take a look at this one here, this is not a straight line. You can see something like look like a curve. Okay, that is looking like a curve, and that shows that is not a straight line. Okay, and you know what? The fact that this look like a curve, it means that we actually you need to use a model. okay, that that have agreement with this particular curve, okay, we actually need to use a model that have agreement with this type of curve, or we can actually do a transformation, okay, and we're going to find ourselves back here, okay. So, but when you look at data set 3, some of them are on a straight line, okay, this is a straight line, but there's an issue right here. If you look at this data point, it's actually far from others, okay, and this data point here actually look like an unusual data point, okay. You remember that part of what we want to do today, when you are investigating assumption, you are not only investigating the assumption of linearity, but you are also investigating whether there is an unusual data point, okay, because when you have an unusual data point, that could actually have a very serious effect, okay, that could have a very serious effect, okay, on the results, okay. So it is advisable to investigate whether this particular data point could have a damaging effect, okay. But let me tell you something, it is not all outlier. You know, we may call this particular, we may suspect this particular data point, okay, to be an outlier, okay. According to Benkamp said, and I quote, an outlier is a data point that is not consistent with the rest, okay. An outlier is a data point that is not consistent with the rest, okay. And we got some outlier that could have a damaging effect, and we also have some outliers that do not have a damaging effect, okay. So we have a way to be able to test, you know, whether this particular data point will have a damaging effect or not, okay. Now take a look at this. When you look at what I have right here, this particular value here fall on the straight line with the rest of the data, okay. The fact that it fall on the straight line with the rest of the data does not make it an outlier, but this can be a leverage, okay. There's a difference between having an outlier and having a leverage, okay. So this actually fall on the straight line, okay. It actually fall on a straight line, okay. But you know what, uh but it's despite the fact that you fall on a straight line, uh is far away from others, okay. We can actually investigate this data point for high leverage, okay. We can actually do that, and that was why so what causes issues in the model fitting, okay. Now I'm going to summarize by trying to say that in the model fitting, we need to look out for these two things, okay. When we successfully put a model in place, we actually need to investigate for these two things. And let me tell you something, uh they are not they don't really come together, okay. As you can see, there is no common point between them, okay. We got a model assumptions violated. We need to investigate model assumption whether assumptions are violated in a model, and we also need to investigate, the presence of unusual observations, okay. So the two of them are not the same, okay, and they need to be investigated one at a time, okay. So what causes issues in the model fitting could be as a result of model assumption violation, and it could be as a result of the presence of unusual data points, okay, that have a damaging effect. So these are the two major things. Even if you have done what you are supposed to do,